everybody, today we're starting antiderivatives. So let's start with what is that? What is our definition? So f of x, and notice this is a capital F of x, is the antiderivative of a lowercase f of x if when I take the derivative of the capital F of x, I get the lowercase f of x. Here I have f of x is equal to x squared plus 3x minus 2. And you should know by now, right, that when I take the derivative of that, derivative of x squared is 2x, derivative of 3x is 3. So you can see that when I took the derivative of capital F of x, I got 2x plus 3, which is what lowercase f of x is equal to. A little bit more to go with that though is that really unique? Is this capital F of x the only function whose derivative is 2x plus 3? So I wrote a couple other functions to show you here. So here's our original x squared plus 3x minus 2. And then I did a capital G of x, which is x squared plus 3x minus 5. And notice when I take the derivative, I get 2x plus 3. Same thing here with this capital H of x is x squared plus 3x plus 750. And if I take the derivative, I get 2x plus 3. What is difference between capital F of x, capital G of x, and capital H of x is the constant. I had negative 2, I had negative 5, and I had 750. We should know by now that when you take the derivative of a constant, it's 0. So you're not seeing that constant when I take the derivative. So it's important that we kind of look at that constant, that negative 2, the negative 5, the 750, and we're going to acknowledge that that's going to happen. We're going to have this constant that might be there, and maybe it has different values. So what we're going to call that is C, and I'm going to use capital C so you can tell what I'm doing. And it's just going to stand for a constant, and we call it the constant of integration. So it says when we do this thing called integration, which is the same thing as doing the antiderivative, there could be an unknown constant. We're going to throw that C in there just to keep track of it. So let's look at some notation. I have the antiderivative of lowercase f of x is written as, so you see this kind of curly sign, so that's our integral sign. And so I have the integral of f of x dx is equal to capital F of x plus c. So we're saying when I take the antiderivative of the little f of x, I'm going to come to the big F of x. Here's our note that we started with. When I take the derivative of capital F of x, I get lowercase f of x. Think of this integral sign here, along with the dx, as being a pair. So every time I have an integral sign, I need to have d something. It could be dx, dy, dt. It doesn't matter. That'll be given with the problem. But they have to be given together. So we say when we do this thing called integration or the antiderivative, we have to say, what variable do I have? Our first rule and our big rule is the power rule. So we had power rules for derivatives, so now this is the power rule for integration. So I have the integral of x to the n dx is x to the n plus 1 divided by n plus 1, then plus c, where n is not equal to negative 1. So let's talk about that. When I did derivatives, I brought the n down and I subtracted 1. I want you to think of antiderivatives as the opposite. So we're trying to come up with the original function given the derivative. So the opposite of bringing a number down would be bringing the number up, right? So I'm going to increase it. So the n minus 1 that we used to do, now we're going to do plus 1. We used to bring the number down, which was multiplying. So what's the opposite of that? It's dividing. So whatever I have as my power, add 1, divide by the same power. So you will see this match between the n plus 1 as the new exponent and the n plus 1 in the denominator. N is not equal to negative 1 because think about, if I have negative 1 plus 1, that would be 0. And then I would be saying divide by 0. So I would have like x to the 0 divided by 0. And we know that's a big like no in math. We never divide by 0. So we're not going to use negative 1. So let's do multiple examples of what this looks like. So the first one I have is the integral of x cubed dx. So I said, okay, my power is 3. Let's raise it 1. So I raise it 1. That's to the power of 4. I divide by the same thing. So those two match, and I say plus c. Let's keep in mind, what are we doing? We are finding a function whose derivative is x cubed. So you could check this. You could say, hey, if I take x to the 4 divided by 4 plus a constant, and I take the derivative, what would I get? It may help to say, well, that's 1/4 x to the 4th. Plus c, and we're taking the derivative. So the 4 would come down, which cancels the 1/4. You would get x cubed The derivative of c is 0, so you can see I got what I started with. That's what you want to do. The whole idea of the dx is if that had been like a y, say I had y to the 4th dy, then that time I would make the power of y go up to 5. I would divide by 5 and I would add c. So just think of this as a check, and I'll make sure we talk about that more. The integral of x to the 6 dx, I add 1 to 6, which gives me 7. I divide by 7 and I add c. You have choices of how to write this. If you would like to write this as 1 over 7 x to the 7, it's just a matter of preference really. So if you like to see the fraction separate from the x, then you can choose to write it that way. When I look at x to the 8th dx, I take the integral, which means I add 1 to the power, that's a 9. I divide by 9 and I add c. Of course, we're going to come along some that aren't as pretty and aren't ready to be integrated right away, so you have to rewrite. So this one that says 1 over x to the 5th, I want to write that as a power, so my power is negative 5. Slow yourself down enough to remember negatives kind of go backwards. So when I add 1, it becomes negative 4, divide by negative 4, and add c. As far as notation goes, you could choose to take this x to the negative 4 and put it back into the denominator, which will be positive 4. This 4 that was in the bottom would stay in the bottom, and then that negative, I would put it in the numerator. Let's look at some more that we would want to rewrite, like the square root of x. Well, remember, the square root is the half power. When I add 1, 1 plus a half is 3 halves. Now you're going to divide by 3 halves and add c. This one, you do need to rewrite it. This is a complex fraction. So I have a fraction in the denominator, which is really not what we like to see. So when you divide by a fraction, you multiply by the reciprocal, which means it turns over. So I have 2/3 x to the 3 halves plus c. Do you see again how you could check this with the derivative? If I take 2/3 x to the 3 halves plus c, and I take the derivative, you can see 3 halves and 2/3 are going to cancel. So you would have x. When I do 3 halves minus 1, I get a half, and the derivative of c is 0. So I can see that I could get right back to where I started if I decide I want to check it. I wanted to do a second one kind of like that. This is the cube root, which means I have x to the 1/3. So again, I add 1. 1 plus a third is 4 over 3, and I do say you do need to write it as a fraction. Don't try to do a mixed number like 1 1/3. You'll never see it written that way. I divide by the same number, so the same exponent goes in the denominator, always plus c. I'm going to flip that 4/3 over. It's going to become 3/4. I have x to the 4/3 plus c. As far as the exponent goes, you can leave it that way. I would leave it that way if you wanted to see what else it would look like. It is still the cube root, but the power inside is now a 4 plus c. I think I would leave it here as this first one, but you can write it either way. Of course, there are more rules, but these rules are kind of nice and I think kind of intuitive. I think you would do it even if I didn't talk about it. So the first one is just what happens with a constant. So if I have this constant that is being multiplied by the function, so it's a coefficient. So I have the integral of k times f of x dx is equal to k times the integral of f of x dx. What does that say? It says if you have a coefficient, you're just going to hang on to that coefficient. You're not going to do anything with it. You're just going to keep multiplying. Then I have the integral of f of x plus or minus g of x, saying if I'm adding or if I'm subtracting, I'm going to do the same thing. I could look at the integral of f of x, then I could add or subtract, whichever one I'm doing, the integral of g of x. The last one is a specific instance of the power rule because I just have a constant dx. So this constant, I'm going to give it an x. What does that mean? So it's kind of like I had k times x to the 0. Remember, x to the 0 is 1. I'm still doing the power rule. It says my power was 0, so add 1 to it. Divide by 1, so I would just get kx. I think it's really helpful to just think of this when you have k, give it an x. In general, I also think about integration as passing out x's. So whatever power you have, give it another one, right? So that's what I'm thinking. When I'm looking back at my function, I should see the power has gone up. So let's do a few more integrals with these new rules. So the first one I have is 8x cubed dx. So I keep the 8. X was 3. I make it power 4. I divide by 4. I add c. 8 and 4 cancel. That becomes a 2x to the 4th plus c. Again, you could check this. If I take the derivative of 2x to the 4th plus c, 4 comes down. 4 times 2 is 8. I subtract 1 from the power, so now that's a 3, and the constant goes away. So I'm right back where I started. Try again. I have 3x squared plus 4. So here I have two things. 3x squared, increase the power to 3, divide by 3. The 4, all by itself, I give it an x. That's what I want you to think with the constants by themselves. Just go ahead and give them an x, and then I have my plus c. You do want to cancel, make it a little bit better. The 3's cancel. I have x cubed plus 4x plus c. And again, check it. X cubed derivative is 3x squared, 4x derivative is 4, c goes away. Let's do one where the numbers aren't as pretty. So I have the integral of 5x squared minus 7x minus 9 dx. So I have the 5x squared. I'm going to increase the power to 3, divide by 3. 7x, I'm going to go from power 1, and you may want to write that in there because this is new. Power 1 goes to power 2, divide by 2. The 9 becomes 9x, and then you have plus c. So I have 5x cubed over 3 minus 7x squared over 2 minus 9x plus c. That's perfect. Leave it alone. Let's throw one a little bit different. I have the integral of a half of x plus 6 over x squared dx. Rewrite that. I'm going to leave it as a half of x, maybe write it as a power 1. I think that's helpful. And then let's say this is 6x to the negative 2 to write this as a power rule. So the 1/2, leave it alone. X, raise it to the power 2, divide by 2, plus 6x, now raise it, it's negative 1, divide by negative 1, add c. This can and should be simplified. So this 1/2 times x squared over 2 becomes x squared over 4. I just multiplied 2 by 2. The 6x to the negative 1 over negative 1, this negative overall says let's subtract this in between. The 6 I'm going to keep, and the x to the negative 1 I'm going to write in the denominator, and then plus c. This next problem, and I actually wrote it kind of twice, shows you why I have to write dx or dy or whatever I want you to use. So when I look at the integral of 5 dx, remember it's a constant, I'm just going to give it the x plus c. If instead I had written the integral of 5 dy, then y is what I'm integrating with respect to, and I would want to write 5y plus c. So that dx or that dy is really important so I know how to integrate what I'm given. I'm going to continue to make this a little bit bigger. I want to throw in some multiplication and division, and there's kind of like good news. There's not a lot of rules for integration. So there's not a product rule, there's not a quotient rule. What you need to do is simplify. So I'm going to multiply x times x minus 5. So I'm going to have the integral of x squared minus 5x dx. Now I can apply the power rule. So this is x cubed over 3 minus 5x squared over 2 plus c. It's important that you first multiply before you integrate. You would not get the same thing if you tried to integrate first and then multiply. So simplify before you use the power rule. Here I have 12x plus 6 over 3x cubed. So this time I want to divide. I'm going to write it the long way. 12x over 3x cubed plus 6 over 3x cubed, and then dx. Simplify some more. 12 divided by 3 is 4. This is x to the power 1 over x cubed. When you divide, you subtract exponents, so I have x to the negative 2. 6 divided by 3 is 2. I have x to the negative 3 dx. Now, I haven't integrated yet. The powers changed because I divided, so now let's go ahead and integrate. So I have 4. X increases by 1, so it's negative 1, divide by negative 1. The 2, x to the negative 3, I add 1. Negative 3 plus 1 is negative 2, divide by negative 2, add c. This could simplify a little bit more. 4 over negative 1 is negative 4. The x to the negative 1, I'm just going to write that over x. 2 divided by negative 2 is negative 1. And the x to the negative 2, I'm going to change that to x squared and say plus c. Here's another one to multiply. X minus 4 squared. X minus 4 squared is x squared minus 8x plus 16 dx. When you square a binomial, you get a trinomial. I used a rule there, so I said x minus 4 squared. I knew to square the first term, I knew to square the last term. I multiplied x times negative 4 times 2, I got 8. If you don't remember that, which is perfectly okay, you write it out. So you can say x times x is x squared, then you have minus 4x, and then you have minus 4x again, and then you have negative 4 times 4 is 16. So I used a shortcut. Now you can integrate. X squared is x cubed over 3. 8x is 8x squared over 2. 16, you just give it an x plus c. So look at all the powers went up. 2 went to 3, 1 went to 2. This didn't have an x, so I give it 1. One little piece could simplify, so I have x cubed over 3 minus 4x squared plus 16x plus c. So I put a couple in here for you to try, and my idea is you try it without me talking. So you pause the video and you try a couple to see if you're getting it before we go on to a few more rules. When you're ready, you come back and watch, see how you did. So I'll start with the 4x minus 7. I'm going to make that 4x squared over 2 minus 7x plus c. One little step of simplification, I have 2x squared minus 7x plus c. For x cubed plus x squared plus 8x plus 2 dx, I get x to the 4th over 4 plus x cubed over 3, 8x squared over 2 plus 2x plus c. Again, one little step of simplification, x to the 4 over 4, x cubed over 3, 4x squared plus 2x plus c. One last you try. I have, this is 8x to the negative 5 dx, so always rewriting to make it a power rule. Now this 8x, when I add 1, it becomes negative 4. I divide by negative 4, I add c. 8 divided by negative 4 is negative 2. Then I have x to the negative 4 plus c. You can also write that as negative 2 over x to the 4th plus c. A couple more rules that we need to talk about. Our rules for e to the x and 1 over x. Remember earlier I said the power rule x to the n works when n is not negative 1, so we have to say, well, what happens if we have negative 1? What are we going to do? So the rule for e to the x is the integral of e to the x is e to the x plus c, which is nice. E to the x, when I took the derivative, was still e, so when I integrate, it'll still be e. The rule for 1 over x is it becomes natural log, and hopefully you remember when we took the derivative of natural log, we got 1 over x. When you take the integral of 1 over x, though, we call it the natural log of the absolute value of x plus c. This is because we can only take the natural log of a positive number, so we want to make sure we have something that's correct when we go to maybe put a number in later. So the absolute value is there. Not the biggest deal to me in the world that you do it, but I will write it because it is technically correct. So let's try a few examples of that. Let's start with 4e to the x dx. It will be 4e to the x plus c. Even if I make it bigger, so I have the integral of e to the x minus 3, it will be e to the x. The negative 3 is going to pick up an x, and then I have plus c. So the power rule is still there for things that are not e, but e to the x just stays e to the x. 2 divided by x. Let's rewrite that as 2 times 1 over x. I think that's helpful maybe to separate the 1 over x. That way you'll see, oh, 1 over x, that becomes the natural log of x. I'm supposed to put in an absolute value, so I'm going to. If you have a hard time picking up on the 1 over x, because I know this is all new, I think you'll see it anyway, because if you tried to make this 2x to the negative 1, you're going to get to the part where you write 2x to the 0 and you divide by 0 and you're like, oh, I can't do that. So you should be able to catch it. When you catch yourself, you're like, yeah, that's right. There's a special rule for 1 over x. It becomes the natural log. There are some fun rules with natural log that can be used to write this differently. So I want you to see other ways this could be written as the answer. Remember how there was that rule that the natural log of m to the p is p times the natural log of m? Well, that could go forward or backwards, right? So written this way with the 2, if I wanted to, I could bring that power up and make it x squared. Then x squared is always positive, so you could just drop that absolute value and call it plus c. This is not a hard and fast, like you have to do this, but I want you to know it might be done. You may see this happen. You may see this written different ways. So I don't care which way you do it. Like they're both the right answer, but I want you to see this is a choice, is to bring that power up. The integral of 6x plus 3 over x. We need to divide 6x over x, 3 over x, dx. The 6 over x just becomes 6. And I'm going to again separate 3 and 1 over x. So integral of 6 is 6x. I have the 3. I have the natural log of the absolute value of x plus c. Now let's check out this 1 plus 1 over x plus 1 over x squared plus 1 over x cubed. Again, a rewrite will help us. I have 1. I want to keep the 1 over x plus, I'm going to make this x to the negative 2, x to the negative 3, dx. The 1 just becomes an x. The 1 over x is natural log of the absolute value of x. X to the negative 2 becomes x to the negative 1 over negative 1. X to the negative 3 becomes x to the negative 2 over negative 2 plus c. I can make this x plus natural log of absolute value of x. X to the negative 1 over negative 1 is negative 1 over x. X to the negative 2 over negative 2, I can make that x squared go to the bottom, the negative 2 stays there, but I'm just going to move it up to the top so I can make that x, natural log of x, minus 1 over x, minus 1 over 2x squared, and then of course plus c always.